Okay, so welcome back to our afternoon session. And our second speaker will be Professor Ivan Cherednik from the University of North Carolina at Chapel Hill, who will tell us about the Riemann hypothesis for the plane curve singularities.
Thank you. Thank you very much. Thank you for the invitation. So this is just an abstract, improved versus the version which is posted here. Let me just mention the characteristic zero. So everything which I will do in characteristic P can be transferred naturally, you will see, to characteristic zero, which is quite interesting. This is connected with the transfer theorem in fundamental lemma. But let me stop talking now before the definition. So my aim is to supply you with absolutely solid definition of super polynomials. The whole story will be about super polynomials. And here we are, right? 4 blocks and 4 different definitions of super polynomials. So we will talk about this particular, mostly about this particular block and about this block. But still, let me say a little something about Daha super polynomials. They will occur. So this is the first definition of Daha is based on band G of elliptic curve. And this definition gives pretty much immediately the action of PSL to Z because of elliptic curve here. Another conceptual definition is using K-theory of affine flag varieties, K-covariant theory of affine flag varieties. And this is really interesting. It gives immediately the polynomial representation, practically immediately, but no action of PSL to Z. And this definition, its demerit is that the polynomial representation of Daha, which is just direct from Fock representations of Heisenberg and so on and so forth here, right, cannot be seen immediately from this definition, but PSL to Z can be seen. Many people try to use K-covariant theory of affine flag varieties to find PSL to Z. It appeared to be almost non-doable, actually. Because Fourier, the main point is that Fourier transform transfers polynomials to delta functions, which is doable, of course, in modern algebra, in some deconstruction, DB constructions here, but still appear to be a difficult problem. But we need both. So let me give you just one line definition of the corresponding super polynomial. So you do the following. First you take a McDonald polynomial in spherical normalization. Simple to define, but let me skip it, right? Then you use this definition and apply, it is only for toric nodes, apply the corresponding matrix associated with toric node here, just PSL, SL to Z matrix here. Fine, you'll get an operator, of course, automatically, right? Then do the following. Consider the matrix entry, one matrix entry in the polynomial representation, the end of the story. That's it, right? Then immediately there is a theorem that you will get a QT polynomial. In this construction, McDonald polynomials provide colors. The matrix PSL to the matrix provides, of course, the torus node. This is actually very close to what Mina Ganagich and Shamil Shakirov did, but they decided to use rules of unity, and they immediately created a lot of problems. They used explicit action, PSL to the action, in perfect Daha modules here. This is really unfortunate because, first of all, you need to connect, was unfortunate, now it is resolved. You need to connect different rules of unity. Connecting different rules of unity is like connecting different levels in Cosmode theory. Doable, but with extreme difficulties, right? The second problem is famous or infamous. McDonald polynomials are infamous because they have denominators, and denominators behave badly at roots of unity. Anyway, just a bunch of problems, right? But still it was resolved in this definition, which is literally exactly the definition. Then Vanya Danilenko and myself, we extended it to torus iterated nodes. This is the generality here, the class here. This class is unlimited. Potentially any nodes, any links with some reservations. Here we can do now with Vanya Danilenko and with Ross Elliott, we can do what? We can do torus iterated links, but colored by any Young diagrams first, and links. Links is important. Links always create problems for Havan-Frazansky polynomials. Colors too, actually. But I will say a little something. I will have, presumably, I will have some time to connect these two approaches here. Daha super polynomials will be mentioned. Is exactly why I spent some time to define that. Again, one line definition, right, with some extras if you move from torus nodes to iterated torus nodes and then to links. And again, there is some potential with some super polynomials are for type A, but pretty much the same is expected for series B, series C, series D, and even for magic series due to the ring growth. Okay, so let me just again emphasize that we have something really rare in mathematics, 4 different definitions of the same objects. And this is not the end. There is a periodic story when instead of Q gamma function, which is so much important here, or dialog here, we use periodic gamma and something like Kubota-Leopold L functions, right? Periodic block somewhere here, right? Then there is another block which is very interesting. You consider Schottky uniformization of singularities and calculate zeta function of the corresponding Dirac operator, right? To more blocks and physics block, I'm supposed to mention it, BPS states. BPS states are rigorous but very difficult to calculate. So you can use BPS states. Now it is physics story here, and then presumably 1, 2, 3, 4 plus 3, 7 different definitions of the same object. Something like this never happened in mathematics. 7 really different definitions. But let me explain the rationale, why we believe that all of them give the same. Because for each and every block here, we expect or we can prove that the corresponding super polynomial, sometimes L function, give complete moduli of topological singularities, right? So this is here. It is a theorem. Here it is just by this manifest here, right? Because we are doing topological invariance here. So if you have such a theorem, then of course expect that all 7 will give you the same, and the rest is just some nice algebra how to go from one to another. This is very much different from algebra, from algebraic geometry. In algebraic geometry, you can prove that if you know classical question. So what we know if you know zeta function of a manifold, of algebraic manifold? The answer is not too much, actually. So Nick Katz proved long ago, not long ago, maybe 15 years ago, more than this actually, proved that if you know zeta function, at least you know virtual Hodge numbers, right? Good, but definitely not sufficient to recover the manifold. Many manifolds have coinciding zeta functions. This is LGOM, but if you go to singularities first, then to topological types of singularities, then you can count on something unbelievable. Zeta function will give you your manifold. Manifold, of course, with all this isotopy equivalence and so on and so forth. Okay, just to explain what happens here, right? And this is good news. But bad news is that when you go to surface singularities, not much from this picture will survive. So this will definitely survive. It is exactly why we'll discuss Mativik. Mativik will survive definitely the story, right? This good news is that presumably Daha will work, right? Here we have big questions. So what to do with this block, with categorification when you go to surfaces, right? People try, of course, many people. Okay, this about it here, right? And let me just go directly as quickly as possible. I will take in consideration the lessons from the previous talk. And we'll supply you first with definitions, right? Then we will see, right? If I have time, I will discuss many interesting things, many exciting things. Okay, sorry, Grisha. Okay, sorry, let me go back, right? Here we are, the beginning of division will take just 3 pages, right? And then you'll get Mativik super polynomial in full generality, which means they are connected with affine Springer fibers that we will cover the most general case of affine Springer fibers. Just using 3 pages, sorry for this dense pages, but I believe they're more or less readable. Okay, so the beginning of the story, we need to fix the base field, which will be C, and a bit later FQ, final field with Q elements here. K, kappa will be the number of branches. Immediately we'll begin, we will do links, not nodes, but links. Okay, technical definition, let me introduce OI, just formal series in terms of one parameter Zi, f of Zi here, f can be either C or FQ later here, and then idempotence, and here we are, we have the ring, which will be exactly this scene for us, right? So everything will happen inside this particular ring. Super polynomials exactly require this uniformization ring. This is classical. The name of the ice here are uniformizing parameters. Okay, perfect, right? And then standard notations. Letter Z means the sum of all of them. The i's are exactly, then they will be just projections. Z times the I times idempotence. Unit is of course the sum of all idempotence. E or simply 1, like here, right? So we're done, and then we come to the one of the key notions in singularity theory, I'm supposed to say, but for curves, at least for curves, the notion of the semi-group gammas. Very simple definition, but extremely powerful and with a lot of applications. So what is gamma I? Consider order with respect to the I of f. F can be arbitrary from this particular ring, right? Or if you wish, project it onto this component and see what you can see, right? Just order, right? Negative, positive, but we'll consider only positive guys here. Clear, right? Immediately there is a question, so what, even now, what is the connection with tropical geometry? There are connections at several levels, but basically, for me, the valuation of 0 is infinity. In tropical geometry, it is like minus infinity. But there is something more serious. So I'm doing singularity. Normally, if it is about amoebas, what Grisha is doing here, they need the whole curve, actually. They need the curve to know it asymptotically, etc., etc. I know, you know, and I know this, right? But still, Grisha needs the curve. For his valuation, right? For my valuation, it is perfectly adjusted exactly to study singularities. And you will immediately see a very powerful classical theorem how these guys behave. Again, what is this guy? Semi-group. What else? Nothing else, right? Just semi-group. The sum of two elements, because we have the product of valuations, is exactly belongs, if they are from gamma, they will belong to gamma. I will provide you with examples, torus knows or whatever, just a little bit later. Okay, now let me go just without no new definitions. Let me go from this setting to plane curve singularities. So first of all, we will consider R's which are generated by two numbers, x and y, with one, of course. One is here, right? So two generators, definition of plane curve singularity, very simple. So we always assume, of course, that localization will, the ring of fractions will be the whole thing. Always assume that this is isolated singularity, right? Okay, perfect, right? So you have fi for xi, yi, many of them, right? And a simple claim, just because of these smart notations here, is that if you consider the product of these guys here, it will be the minimal equation for x and y, just because of the identicals, right? You need to play a little bit with this. If you apply fi, you will kill only ei. Then you will kill e2, etc., etc. So this is a smart way to introduce this particular equation. But there is some limitation, immediate limitation, pretty much classical in the story about curve singularities. We assume that they are non-proportional. Why? Because then there will be next page. Because if they are proportional, they will be seen not seen topologically. You will intersect it with something not seen topologically. So classical constraint, practically in all old papers, new papers, is that they are supposed to be non-proportional, or technically we say they must be square-free, right? But simply non-proportional. Linear, fine, as many as you wish, but non-proportional linear. Clear, right? Okay, good, 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 good. Then, of course, I need to establish some connection with topology. Let me do it, right? So now f, of course, is C. Then you do something different from what Grisha did before. I intersect classical notion of the link from any manifolds, of course, right? Or from any singularities. You take this singularity, right, for small u and v, intersect it with small sphere, three-dimensional, for surface singularities with S5, of course, and so on and so forth. Here you will get three folds. But if you do this intersection, you will get your link, right? Normally, generally, of course, because we have components here, it will be the link with kappa components. Clear, right? So equation, intersect with small sphere. This is very bad, singular, etc., etc. But upon intersection, it is nice, smooth node here, right? The miracle, which anyway, not exactly the miracle, but the point. Arnold made the point that exactly because of this construction, we have an immediate way to produce nice, smooth manifolds, right, from singularities. He mentioned that maybe singularities, algebraic geometry is supposed to be about singularities, right? No projective, no smooth varieties, just singularities. There are some origin, classical origin. He was not the first, actually. Just to mention Vladimir Arnold, his fantastic contributions to theory of singularities and to many other things, of course. Okay, good, right? So this construction, right? And then we have a powerful classical theorem that then I can give a definition. Topological type of singularity is simply the isotopy type of this intersection, of the corresponding link, right? And immediately there's this theorem, classical, with some non-trivial contribution, especially for links here, right? So it appears that our gammas are exactly the key invariants, but you need to know something else. You need to know pairwise linking numbers, which are just intersection numbers. Okay, here we are, theorem, right? Isotopy type appear to be entirely algebraic in a sense, right? You need to know gammas, entirely algebraic objects, and little something else, but this little something sometimes not simple to calculate. I personally prefer singular or something. Anyway, singular will calculate it for you immediately, right? Everything. So algebra, yes, of course, total algebra. But intersection numbers must be considered seriously, at least because they are not arbitrary. So if you follow this definition, you will see that not arbitrary intersection numbers are allowed. Otherwise, you will get not algebraic numbers here. Okay, so this is theorem. Again, with links, it is significantly more difficult than just to prove that gamma is invariant. Perfect. So we're done here, and then I need, maybe not immediately, but a bit later, I need the notion of good reduction. Again, remember, we're doing singularities up to isotopy equivalence, right? And immediately you see that within a given topological type, always you can assume, of course, that x and y, everything is over z, not over f, but over z. Just deform them a little, why not? Actually, you can assume that they're over z. Again, because of this powerful theorem, there's absolutely no problem with this. Just find this guy, which find the corresponding coefficients of your equations or whatever, right? Just to make proper, to ensure that your gammas are proper, your intersection numbers are proper. And then after this, of course, you can just consider mod p situation. You can go to fq, q will be p to m. You can go to finite field. So there is a sketch of the proof that if it is just a uni-branch, that there are no point of bad reduction. No point of bad reduction means that within isotopy type, you can always make any prime number point of good reduction. But with links, it can be more complicated. I just don't know what happens with the links. But still, it is okay. Of course, we understand that whatever can happen, there can be only finitely many points of bad reduction. So we can continue, but still, it is better than classical algebraic geometry when you need to consider some serious analysis of point of good reduction, bad reduction. Points of bad reduction is quite a problem for the theory of Hasse-Weil functions, for the functional equation, and so on and forth. It was the beginning of my official expert for the Congress here. Quite a serious story. They use semi-simple Frobenius, a lot of techniques. Many people, absolutely fantastic mathematicians, were involved and are involved, exactly because this is not highly involved, actually. What to do at points of bad reduction. Okay. So essentially we're done, but I promise the most general possible definition, so I need to introduce ranks. So technically, the story is exactly about the assumption that we consider only square free. Now let's set multiplicities, right? Multiplicities can be addressed only if you switch from linear bundles to any bundles here. This is exactly what I'm going to do. I'm going to add torsion-free sheaves, etc., of any ranks. So this is how I'm going to address multiplicities, right? And this is exactly why it was so difficult in theory of fine springy fibers, when ideally we are supposed to consider absolutely arbitrary polynomials, but it appeared to be difficult even for this case, right? Which is, if it is just one single f, it is called nil elliptic. From Penk's talk, for instance, right? Elliptic, or mostly we will say nil elliptic to avoid confusion, right? So this is immediately one problem. If there are many of them, like product of FIs, now you understand there are reasons for this because we have topological problems immediately. And the next level and the last level to assume that there are some multiplicities here. Okay, let me show you how to do it. It will just take this short paragraph. So I'm going to enrich accordingly the number of idempotents, right? Namely, first of all, what are these C1, C2, C3, C kappa here will be exactly the multiplicities. F1 to C1, F2 to C2. Yeah, I can of course assume that they're ordered, right? I can just shuffle F1, F2, F3. So these guys, C's, right? C will be exactly the multiplicities of F's here. Then accordingly, let's enlarge. Then this will be new idempotence. right? And Z1 old Z1 or old E1 will be just the corresponding sum of how many C1 epsilon. Epsilon will be new idempotent. Epsilon 2 is not shown here, but at least Z1 is the sum of zetas, right? Zetas are exactly the same components projections of some big zeta here on this particular components. Z2 means the next sequence of these guys here, and the bearings are always diagonal here. Pretty much natural in linear algebra. Of course, it is natural, right? But surprisingly, it works perfectly in spite of extreme simplicity of definitions. Okay, now before this we had kappa zi's. Now with the zetas we have now the number will be the sum from 1 to kappa ci's, right? C1 plus C2 plus C3. Perfect. So we enlarge this particular guy. Now it will be called omega. Omega is a big one. So O is of course diagonally with respect to this Z1, Z2 components here, diagonally embedded. R is old. We don't change R, of course. R is exactly the guy which was defined under the assumption that this is multiplicity free. Okay, let me give you just some time here, right? So what happens? First it was O, right? O direct sum of components here, right? And now we add multiplicities, and eventually, of course, there will be some kind of bundles of ranks C1, C2, Cn, but no bundles because we have singularities. Okay, we're almost done actually, so let me continue. Here we are, right? The key definition of this talk is here, right? So I need just little something, the definition of the notion of standard modules. Standard modules are R invariant F subspaces, of course, always. F can be whatever, right? Can be C or can be FQ. Right now it is, this definition is universal here. And they all, this is interesting, they all must sit inside omega. So we don't consider M's somewhere. For instance, they are not ideals. They're like ideals, but we can say negative ideals, or sometimes they call exactly positive ideals, right? This M must belong to omega. Because omega is a collection of uniformizing parameters. So we need uniformization. This is exactly why I still don't know what to do exactly for surfaces, right? Uniformization is a little bit different for surfaces. Okay, perfect. And then it is standard if it generates over omega, the whole omega, right? If it is the simplest possible situation, when it is irreducible, there is only one F, it is irreducible, then it simply contains 1 plus Z plus something, 1 plus Z plus something, right? So valuation begins with 0. Valuation, the corresponding gamma contains 0. So of course I can immediately spell what I'm saying here using valuations. Okay, this is just to show you what happened if we have no colors. This will be called colors, C1, C2, Cn. Let's assume that we have no colors. And then it is easy to calculate. But anyway, one more notion and I'm ready to proceed. Rank. Rank is Nakayama rank here. You just consider M, right? Multiply M by the maximal ideal of R, which is of course non-trivial, right? Maximal ideal of O is totally trivial, of course, right? It is Z times O. Not exactly maximal if there are many components, but it's understandable. Here you just multiply it by exactly by maximal ideal of R. Here we are. Technical definition is not maximal, sorry for this. This is definition, right? This is exactly the definition. Maximal, of course, if there is one component. Okay, so we introduce, so to say, maximal ideal of R, right? Take M, it is R invariant, so multiply it by MR and see what you can see. This is now finite dimensional space over F. From now on, let's make it FQ, because I will need it here anyway. Okay, let me skip it. It's just to calculate. So what is exactly rank? What can happen with rank? Okay, let me spell it. It's not difficult. So what standard question? What is maximal rank? There is some formula, but at least when there are no colors, the answer is kappa, the number of reducible component, minus 1 plus delta. Delta is a classical Serre number, right? Maximal ideal here divided by maximal ideal O, which is exactly this particular guy, divided by this particular one, right? So let's assume that there's only one component. Then kappa minus 1 is 0, and we will get delta. Delta is, of course, exactly uniformization ring, right? Used to be O divided by your R. This is the simplest, there are several definitions, but this is the simplest possible definition of Serre number, which is arithmetic genus, of course. Nothing else but arithmetic genus. And here we are. So First of all, look at this particular guy. I consider the product. So first of all, rank is necessary. Oh, sorry. First thing first, right? The summation will be over m's, right? M's are exactly standard modules. Then look at the letters. So we have letter T, we have letter A, we have letter Q. But there is no serious dependence on letter Q, unless here, right? Why? Because M, the count of M is exactly the problem. The count of M is exactly the count of problems mod P, right? So the dependence on M, the serious dependence, not like this, but serious dependence, is hidden in the count of M's here. So definitely it makes sense only over finite field here, unless you do motivic, general motivic story when you consider different motivic measures. But we are doing just, in our situation, we are just doing finite field. Okay, let's consider the sum over all standard M's, right? Then this is pretty much natural, right, for all theories of zeta function. We call it Iguza term or whatever, depending on what you are doing actually. So T to dimension omega divided by M, right? The distance from omega, all of them sit in omega. And then here we have this factor, which actually appeared very recently. So this particular story was really renewed dramatically during the last year, including, by the way, my stay here at Benson. Yes, please. Well, absolutely. We will calculate together with you the super polynomial for trefoil, right? Just which is what done. Anyway, you will see anyway. Right? A good question. I understand that it's about time here, but it will be almost next page. So just be a little bit patient. Okay, so this is a formal definition, right? Just one notice that if, as always, if product is empty, it is 1, not 0, right? But this is standard. Okay, then conjecture, and I will be ready to discuss examples, right? Before this conjecture, it was a little bit tricky. So conjecture is that motivic motivic superpolynomial simply coincides exactly with the Daha superpolynomial. Remember, I advertised it as one-line definition here, right? Some co-invariant of some gamma applied to something here, right? So coincides with the Daha superpolynomial, right? But there's some restriction about colors. The colors must be exactly C1 times omega 1. Anyway, rows, only pure rows are allowed, right? As many as you wish. So think about some link, right? And each and every link is colored by this guy, C1 omega 1, C2 omega 2. Only this is allowed because we do only some kind of, anyway, only this kind of colors here. Okay, perfect. Now, whatever you prefer. Examples first. This is some kind of already discussion, right? But maybe you're absolutely right. Let me begin with examples. Here you are. Examples, right? Slowly. This is an involved example, and this is trefoil, which I promised, right? Trefoil we will calculate together, but first of all, let me show you some typical example. Typical example is, of course, non-torus. Typical non-torus example. So here we are, right? This is the case of irreducible, of uni-branch situation, when everything is irreducible. No, absolutely no problems here. So let's do the following. So there will be just one z. X will be z to 4, y will be z to 6 plus z to 7. This is famous example. Zariski liked it very much. The simplest non-torus singularity, non-homogeneous, non-quasi-homogeneous singularity, right? So let's calculate gamma. Gamma is exactly valuation. So 0, of course, right? Automatically, right? Valuation of 1 is 0, right? Then 4, 6, all even numbers, right? Then something will happen. There will be 13. 13 will be because of some interesting trick in this business, absolutely standard, right? You consider here, you consider cube of this guy, square of this guy, we subtract and you will get z to 13. Z to 13, right? So 13 is available, right? But then you will continue, and then after 15, after 16, 15 is the last missing guy here. After 16, all of them will be available here. This is nothing else but Frobenius coin exchange problem for torus not exactly, but with somewhat unusual situation when it is z to 6, not exactly z to 7, but z to 6 plus z to 7. So what is exactly the genus? Well, to calculate the genus, the SER number, you need to consider z plus minus gamma. Here we have all the gaps. All of them, how many? 8. The genus, the SER number is 8, right? Perfect. So what is the corresponding link? Topologically, link is a torus node, trefoil, cap 2-3 or cap 3-2, doesn't matter here, and then cabling, special operation cabling, which I'm not going to discuss. But anyway, you have trefoil, and then you have 13-2 guy on top of it. But it depends on framing. Framing is something which I prefer not to define. Of course, framing is necessary, otherwise it is not clear what I'm saying by some kind of twisting. Okay, so we're done with this example, and then computer program calculate motivic easily, right? And for Daha, it is really some kind of absolutely basic calculation, very simple. You can do it manually, right? Now let's do something which is so it was 15. Oh, I have a lot of time, so only 30 minutes. Let me check with I have 30 minutes. A lot, right? So I learned something from Grisha, but it seems that I learned too much from Kim. Yeah. Okay, slowly. I will slow down. So let's calculate something what Dor discussed, the super polynomial of trefoil. So let me just use a chalk, right? So the famous formula, super polynomial, known absolutely to everyone in topology and QA, right? So super simple formula, but with so many applications. So Q equals T, then it will be Hamfly PT. Hamfly PT. Then A is minus T to N plus 1. It will be quantum invariant, Jones invariant or whatever, Jones invariant for AN of trefoil. T32, right? Alexander, Q equals T, A is minus 1. Alexander polynomial, right?
So, is it somehow related to the A polynomial?
No, this is just, it's better just to say exactly what I'm saying, super polynomial, right? Super polynomial, right? Or triply graded Khovanov-Rozansky polynomial, they coincide. There are some nuances here. So sometimes, anyway, triply graded Khovanov-Rozansky reduced polynomial. Let me give an exact name for this guy, a super polynomial. This is standard notation, right? The name is, by the way, due to Sergei Gukov, if I understand correctly, or his collaborators, maybe rather his collaborators, right? Or it is reduced Khovanov-Rozansky polynomial. Right? Okay, and then classical application. This is the limit to and we keep A here, right? This is the limit to quantum groups. Exactly, this A here. We have actually more of this, but I will discuss them later. But anyway, let me create this picture, right, just to show that we will calculate in a minute, right? It will take just 1 minute. We will calculate something really powerful. And Daha is fine, but with Daha I need to give you some definitions, and still it will take, after definition, it will take like half a page to calculate this particular guy. And moreover, for Daha, we can calculate these particular guys for any root system, not only for AN. And then there will be immediately a stabilization problem, right? Then I will calculate, my computer, of course, can manage it easily, right? Eventually I will get this ultra simple formula. But even with Daha, which I like so much, nature love so much here, still the demerit is that it is like a miracle that the formula is that simple. Even if I know how it works, anyway, I calculate and still it is some kind of miracle. Unfortunately, dependence on A, we have stabilization theorem. Mostly the reference is Schiffman with 0, for instance, lemma for 2 somewhere, right? Stabilization is okay, but it is even difficult to control the degree of A. Even degree of A, here degree of A1, even this thing is difficult to control because we know that it exists, but somewhere. I use deformation arguments here. I can calculate them directly just because of definitions. Okay, so what is good about Daha? Now we can discuss it, right? So Q and T, polynomial depends on Q and T, is manifest just by construction, right? Because this parameter are right from Daha. No final fields here. But with A, we know it is a polynomial, but even degree of A can be a problem. Actually, it is a problem. Okay, but all in all, if you combine everything together, it will be still a couple of pages. Let me show you something which is unbelievable. Absolutely the simplest way to calculate this very super polynomial, but in motivic setting. Okay, so now we understand perfectly this involved example, but this is the simplest possible example. So the corresponding R, the ring, is Z squared and Z cubed, right? Perfect. Gamma, no need to write gamma on the blackboard here, only Z will be missing, right? This is classical coin exchange when you have 2 cents and 3 cents. There are no coins like this, but if they were existed, then of course it would be exactly like this, right? So delta is 1. Of course, it is elliptic curve, degenerate elliptic curve. Perfect, right? So here is gamma, right? Just one, only one is missing. So what are the modules, right? Modules are invariant modules. They can be only, it's very, very simple. They can be only invertible with one generator, which will be 1, and lambda z. What is lambda? Z is free parameter, because z is not inside R, right? So we can multiply it by any lambda. Perfect, right? So invertible, and of course there is an exceptional one. The exceptional one is exactly the whole O. Now the number of generators is 2, with 2 generators. Here we are, right? 1 plus QA, just the previous formula, because of O, and QT, right? T is degree. T is degree here. Oh, sorry. What is, I need to say something, degree. Degree is the distance from O. If it is O, distance is trivial. So there will be no T. Here, distance is 1. So QT. Here we are, right? The simplest possible formula. And to convince you that we can now calculate literally tons of examples, frankly, if it is really complicated, I switch to my Daha software. Daha is better, especially with colors, definitely it is better. But still, for many, many examples, it's just marvelous, right? So literally 1 minute and you will get exactly this guy with so many powerful applications. Okay, so next, in the same style, I have time for this, hopefully, but I will not relax too much, I promise. Let's do the same for Hopf link, right? This is interesting because links are traditionally quite a problem even now for Havana-Frazansky theory. Fortunately, we have Sergel modules and we have recent papers when there is some procedure how to calculate Havana-Frazansky polynomials, how to calculate them for links, right? For instance, about 5 years ago, Hogenkamp, Matt Hogenkamp and Anton Melit, they posted, but without much explanations, posted the formula for double trefoil. Double trefoil was a very, very basic calculation for Vanya and for myself about 5 years before them, and the formulas coincided, right? But still, I wish to look how they calculate, because they decided not to post the calculation, just posted the formula. The formula was correct, both are extremely nice mathematicians, actually my good friends here, but still I decided not to request the calculation. You see, some nuances are important, right? So what they really assume, what is really necessary, but all in all, the program is complicated. The program which they posted, how to calculate it for arbitrary link, is quite complicated, actually. So it's better to see. With colors, of course, you understand, this is uncolored double trefoil, right? Double trefoil is exactly x squared equals y cubed, but you square x and square y. X to 4 equals y to 4, double trefoil, right? X squared equals y cubed, square x and square y. X to 4 equals y to 6, right? And believe it or not, for Havana-Frazansky theory, it is quite a challenge, right? It was managed only recently, right? But for us, it is just regular, this one of the simplest possible examples. The formula is long enough, actually. Don't think that it is. But we will do something similar. Similar, we will do it for Hopf to link, right? Hopf to link is the product. But anyway, this exact definition, right? You have 2 unknowns here, and the linking number must be +1. If it is -1, it is not algebraic. It must be +1. Okay, so how to calculate, right? Just using the machinery I create. The machinery is totally elementary, but of course it takes time to get used to it, right? Again, E1, E2, because we have 2 components, Z1, Z2 automatically, right? So R is, you remember, diagonally embedded. E1 plus E2, which is 1. And then we have X, and we have, anyway, this is R exactly. Z1 and Z2. So this is exactly the definition of R here. And what are the modules? The modules are, in terms of idempotence only, E1 plus A, E2, right, multiplied by R. invertibles in a sense, but they, of course, the meaning is different. And then, as always, of course, there is the whole thing, O, right? So look at this particular guy. So first of all, it must be standard. Standard means that it must generate the whole thing. So the coefficient alpha, both coefficients of A1 and of A2 must be non-zero. Otherwise, they will be non-standard. So this we can make it 1 because everything is up to proportionality. And here we have Q minus 1. So here we are Q minus 1 instead of Q. With Q, it would be trefoil, but now it is Q minus 1 times T plus 1 plus AQ. Pretty much the same calculation. Some kind of uniformity. And then we see the first example when the coefficients can be negative, which is, of course, very much important. So for links, so for nodes, we somehow expect, but exact conjecture is that super polynomials are all with positive coefficients for when the colors are rectangles. It is Daha conjecture, the last unproven conjecture about Daha, intrinsic conjecture about Daha. There are some connection conjectures, but still the last piece is exactly to prove that if the color is rectangle, right, rows, columns, etc., all coefficients are positive. But for links, you see immediately something happens, right? And now I understand why it is difficult for Havan and Frazansky, because they need to address negatives here. For codification, it is no good. You need to divide or multiply and do something. Perfect, right? And then just for fun, I provided pretty much the same calculation. This is, by the way, when you color one of them. Again, very simple calculation. One of them now is colored by M. M multiplied by omega 1. Then example, when you have 3 of them, plus 1, plus 1, plus 1, and one of them is colored by 2 omega 1, right? Enjoyable, right? Enjoyable in what sense? When you calculate it manually, right? Always you miss some terms. It is inevitable. But fortunately, I knew the answer, so eventually I reached the right answer. But it is really some kind of nervous. This is very interesting, extremely interesting Q linear algebra, right? With a lot of Q binomial coefficients, but all in all, you see the length, right? But anyway, it's just for fun. Okay, now we are approaching actually, not exactly the end. I have time to say something about row invariance. But what is the second conjecture? First conjecture, remember, Daha literally coincides with proper colors. Daha superpolynomials coincide with the corresponding motivic superpolynomials. Okay, conjecture 2 is the connection with L functions. There is quite a story. So this Galkin is, of course, not Sergei Galkin, not his father, not his grandfather, the year 1973. Actually, more or less, I know him, at least indirectly here, right? He is still alive and well, but he doesn't do any kind of number theory. But anyway, in 1973, then Storr wrote a very nice paper about the subject. They provided this particular definition. So what is exactly the challenge? The challenge is that they decided to define Z is literally like classical definition due to Tate and to many others here, just p-adic integration. Pretty much solid thing here. Then immediately there is a problem. For singular everything, for singularities, the corresponding zeta function doesn't satisfy functional equation, simply because there is no Poincare duality. So you cannot do this. But there is a smart trick. If you multiply it by 1 minus t, technically, I skip it, but technically you go to L functions. L functions will satisfy functional equation. What is functional equation? Classical stuff, Hasse way, it is t to 1 divided by qt. What is super duality? Super duality is q and t minus 1. In Daha or motivic superpolynomials, you can exchange them like this. And then there will be some coefficient of proportionality, super duality. Of course, they are different, but on the other hand, this will be addressed in a very simple algebraic way. Let's do the following. Let's consider motivic superpolynomial. And let's simply brutally replace q by qt. This seems to be very simple, but it is based on the conjecture that motivic superpolynomials depend on q polynomially, which is not known. Right now, I can prove it in some cases, for instance, with 3 generators, but still it is an open question. The second open question about motivic superpolynomials is that they are topological invariant, still not known. So this is the demerit. Fantastic merits of motivic polynomials is that you can calculate in no time quite complicated examples. But demerits that we still don't know some basics, right? Especially the dependence on Q. That they depend polynomially on T and A, just by construction, right? But not on Q. Daha, Q and T manifest, but with A, some kind of theorem, right? But if you combine them, you really can do a lot. So again, let's do the following. Let's consider motivic QT, just plug in QT, or introduce Q nu, which will be exactly the one from FQ, Q over T. Okay, so here we have an entirely algebraic conjecture that motivic upon this substitution coincides with L. Right? Looks like an algebraic statement which can prove algebraically with one reservation. This is a very strange substitution. It requires some highly non-trivial substitution, which requires some conjecture, definitely. Otherwise, we suspected, not only me, Davesh Malik, we suspected this can be proved like this, right? It didn't happen, didn't materialize. Mostly because we have a non-trivial substitution here. And the second is very interesting. If A is special, -1 divided by Q in this notation, generally minus T divided by Q, then you will get L principle. I need to explain. So what is L? L, Z, what is Z first? Z is pretty much the same sum, but you consider the sum over ideals now, right? No uniformization, which is good. And of course, automatically, because they are ideal, you replace dimension O or omega divided by M by R divided by M. So sum over ideals. But this term is absolutely unchanged, pretty much the same. Clear, right? So now it is about ideals, good, because we have a Hilbert scheme, stuff like this. No need to do a uniformization. And then, but on the other hand, if you define any kind of zeta, there are always two choices: summation over all ideals or only principal ideals. This is if you do principal ideals, it's called Zuniga zeta function here. So then the conjecture is for arbitrary Gorenstein rings that if A is -1 divided by Q, then you will get here you will get coincidence. This is the first true is only for plane curve singularities. But the second presumably works for Gorenstein. Again, as I already mentioned at the very beginning, all this stuff works for in characteristic zero, all definitions. So what we'll miss? There will be no Gorenstein rings, of course, in characteristic zero. First. Second, no projective anything, no compactified Jacobians, but I don't need, instead of Gorenstein, I have explicitly plane curve singularities. In arithmetic, I mean arithmetic of characteristic zero, in periodic arithmetic, this is just fine. And then I don't need exactly the structure of projective varieties because I'm doing motiving things. I need stratification only. I don't care that there is some global structure of projective variety. Okay, just to go back to what I already almost promised. Okay, so now Alexander polynomial in full detail. Using this conjecture, right, you will do the following. I already explained. Let's simplify our life here. There will be only one component. And Q will be 1, tends to 1 to be exact, and then you will get exactly, according to this table, you will get exactly the formula, general, absolutely general now formula for any algebraic knot of Alexander polynomial. Very easy to explain, because here Q will disappear, Q is 1. So there will be no non-trivial contribution of M's here. So there will be just summation of these T's. You need only to know what are the dimensions here. And here we are. The formula is just summation of T nu when nu are exactly from gamma. Of course, it is topological invariant because gamma is the only topological invariant. So here we have the formula, right? And it is obviously it is topological invariant. Just summation of T. It is a series, of course, because it is Z here. Then you multiply it by 1 minus T, and you will get classical formula for this formula for Alexander polynomial for arbitrary algebraic knot here. You see how simple it is, and then let me show you the picture of pretty much the same picture here. So what really happens? So first thing first, T equals Q, exactly how fly PT. Here, let me skip quantum groups. If T equals Q, A is -1 is Alexander polynomial. And this is very interesting. When A is minus T divided by Q, then it is the passage to Higard-Floer cohomology. Pretty much everything we know is about these particular three cases, right? Alexander is some expression, some degenerate. Okay, then how much time do I have? 10 more minutes, right? A Riemann hypothesis, right? Once you have functional equation, let me recalculate it to the classical Hasse-Wiley equation, T to 1 divided by Qt here, right? Then immediately there is a question. Do we know that all the zeros, T zeros, with respect to T, Q is fixed? Q is fixed, it is just we can change it as cardinality of affine field. But a bit later it will be not cardinality, but Q is a constant, structural constant. Then a question, is it true that absolute value of any zero is always 1 divided by square root of Q? They belong to the unit circle here. The answer is yes, it is true. I proved it recently for sufficiently small Q, but I proved it only when A is 0. Conjecture is it true for any A coefficients. So yes, it is true that for sufficiently small Q, all zeros belong to the unit circle in some non-trivial way, but strong version of this conjecture is that the bound for any algebraic knots is 1 divided by 2. So this is exactly the story about Riemann hypothesis here. So what is really remarkable here? Let me just do some informal comment. Remarkable is that this particular bound by the 1/2. First, what Witten and many others did periodic strings, especially his observation that Frobenius becomes Dirac operator when Q tends to 1. What is Q? Q is cardinality, like for me. Q is the cardinality of affine field here, right? There are quite a few physics story here, but his observation was that when you tend Q to 1, then Frobenius morally, not only morally, sometimes technically, becomes exactly a Dirac operator, right? But when Q is 1, we go below 1. This is 1/2 now, right? How we can do it? Because Q for us is a parameter. We have conjectures, sometimes theorems, that our super polynomials depend on Q polynomial. So we can examine this particular case. So here we are, and then something really interesting happens. So I know when exactly this bound can be reached, 1 divided by 2. And then the more, really something mysterious, the more complicated our knots, the better this bound, right? So in the beginning, can be sharp, right? But then after some unfortunate, we can say, right? Unfortunate knots, right? Then it is getting reasonably good, right? Think about elementary particles, right? If Q is 1 divided by T, like in physics, you know, right? Then,
so many polynomials. Which of them are
guys, there are some mysterious oscillations. When your knots are getting more and more complicated, right? Somehow Q is getting better, not worse.
Are they defined for arbitrary knots or for algebraic ones?
Only algebraic in this business, only algebraic, right? If it is non-algebraic, nothing works here, just nothing, right? There will be no Riemann hypothesis. This is pretty much inductive. If it is a non-algebraic, there is no single case when there is Riemann hypothesis. It's like 1-to-1, you know, right? Only for algebraic use. Good question, right? And the answer is only for algebraic. Okay, so anyway, the story is that they are getting more and more complicated, mathematically speaking, because of some oscillations which I can't understand, of course, some kind of, then Q is getting more and more liberal, right? Physically, it is like the chances to see some elementary particles which are complex are bigger, right? Of course, it depends on the temperature, but we're at the corner of universe when the temperature is practically 0, not absolute 0 so far, but eventually it will be absolute 0, of course. But anyway, a really cold corner of the universe, right? Used to be some crazy temperatures, Q is like 1/T, right? In the beginning of everything, when all elementary particles could be seen, right? Not exactly elementary particles, but the corresponding Landau-Ginzburg theories for superpotentials, which are exactly the equations of singularities, to be a little bit more correct here. And then something happens, and right now we can see quite a few of them, but not all of them, and eventually we will see practically nothing, right? Absolute zero. But this is just an illustration, right? Absolutely irresponsible. But what is responsible? I have time. Let me see how to use it, right? Better quasi-row. Let me just mention, right, because it requires some special discussion. Let me mention that, surprise, surprise, it appeared that pretty much the same super polynomials serve absolutely different kind of geometry. Namely, geometry, there is a so-called row AB invariant, right? Of course, we somehow we like very, very much knots, links, Havana-Franzansky theory, but still there is a different piece of geometry, which is like 90% of geometry. When people study Atiyah-Paturi-Zinger invariants, all of them, determinants of Laplace operators, indices, etc., etc., etc. Classical geometry is mostly about this. So what is exactly row AB? You consider, first of all, this is our three-manifold, odd-dimensional manifold here. So let's assume this knot, then it will be Z, abilization map to H1, right? Then do the following. Consider literally Atiyah APS invariant, ET invariant, right? for twisted for this manifold twisted with this bundle, with this line bundle, and divided by the classical twisting. Divide and you will get exactly the graph. Exactly. Then let me show you. So this is exactly how to obtain them from super polynomials. But let me show you the end of the story. The end of the story that I calculate super polynomials. This is the formula for cape mn, cape sr. I give you one example at least of this particular guy. So this is classical formula for rho AB invariant. Rho AB invariants have many applications, including, by the way, Yao Bogomolov, Yao inequality, lots of applications everywhere, including algebraic geometry. Different kind of geometry anyway, right? Nobody expected that there can be quantification just because here we have coefficient minus 1 divided by 3. What to do with this, right? And this is reasonable. Then I calculate with my super polynomials with some substitutions. Look at this particular guy. It is exactly what I obtained. So no minus 1 over 3, but there is coefficient 1 divided by 24. But 24 is absolutely not mysterious. There is a standard exercise, actually, I will add it to the second edition of my book in elementary mathematics here, that if mn are GCD1, then this particular guy is divisible by 24, right? Nice exercise, really nice, right? Absolutely, of course, trivial. So here were some discrepancies, but pretty much the same formula happened, you know, right? So, and this can be categorized because these numbers are integers. Okay, so let me skip it completely. And still let me say something about the history. I have 3 minutes, right? Maybe it's a good time to invest 3 minutes, right? To show you the origin. The origin is the beginning of modern enumerated geometry, so to say, right? I believe the origin was exactly this formula. Due to Gopal Kumar Vafa and Panharipande, Rahul Panharipande and Thomas, right? So what they calculated, they consider C2n Hilbert scheme, or simply 0 cycles, right, of total co-length n, right? Hilb, of course, Hilb n, right? Then consider earlier characteristic, earlier numbers of this particular guy, and the generating series, right? Theorem number 1. This guy is actually rational. Rational means that this is not an infinite series, you can make it finite. If you look at this formula, I just copied it from the source here, you will see that mostly these guys are negative, so actual denominator is 1 minus q divided by square. So the point is that if you multiply it by 1 minus q squared here, you will get a polynomial, right? So first stage, it is absolutely applicable to me. Instead of some series, right? Khovanov-Rozansky generally are series. The reduction procedure is quite unlocked, actually, right? Normally, Khovanov-Rozansky, practically always, Khovanov-Rozansky polynomials are series, not polynomials. First theorem is supposed to be that upon some substitution and renormalization, they are polynomials. Good, right? So we're done here. Second level is much more subtle. If true, you need to prove that these particular coefficients are from Z plus. Then it is really enumerative geometry. Then there must be some problem, right? Combinatorial, algeom, or whatever problem here, and so there must be some reason for this guy to appear. This appeared to be really difficult. First, Goethe did it for the top coefficient. Then Vivek Shende finished the story for all i's using a very interesting technique, versal deformations and real theory. So he managed to prove positivity. So this is exactly to show you the origin, right? Then the story was Oblomkov-Shende conjecture, Oblomkov-Rasmussen-Shende conjecture. And the end of my talk, I have 1 minute, right? So this is exactly to spell again what we already discussed, just an attempt to compare merits and demerits of the Daha approach, right? Which is definitely from superconformal field theory. Daha is actually the true origin was not because of geometric stuff. It happened later here, but the origin was Kesey, the theory of Kesey equation. So certainly it is superconformal field theory. By the way, 2 different definitions are the first definition is Coulomb branch here. The second is Higgs branch. Daha is self-dual objects for this particular duality. But anyway, Daha is superconformal field theory, right? Then, as we already discussed a little bit, motivic stuff is definitely Landau-Lifshitz, Landau-Ginzburg sigma model, right? Superpotential is exactly the equation of singularity. So here we have some link from superconformal field theory to Landau-Ginzburg sigma model here. This is absolutely the main topic of modern string theory, actually of all levels of string theory, due to Maldacen and due to many, many other people here. Here we have a solid link and S duality, so much famous S duality, becomes a literally functional equation. Okay, so then one more remark, right? So let me skip it completely. A recent observation that we not only super guys here, but even quantum, Daha-Jones and guys are motivic. But let me skip it completely. And the end of my talk, perspectives. Perspectives is exactly what I said about surfaces. So we really need, because of many reasons, we need to go to good, at least good isolated surface singularities, right? So what can be done? So motivic is difficult but doable. This is exactly what I spelled here, right? So motivic means that you calculate Hilbert schemes and see what you can see. Klein singularities are just fine, right? Second, Daha. So good news is that potentially Daha as such, without any changes, can be used here, right? And then, of course, if you go from super polynomials to super series, right, you have all the reasons to expect L functions, zeta functions to occur. This is exactly our super destination of this super story here. But here, not much to report. Thank you very much.
Okay, any questions to the speaker? Yes, please.
Super duality.
Yeah, can you explain how do I see the super duality in this typical example for the triple knot?
Slowly. So super duality means exactly this particle. This is Daha parameters, right? Nekrasov parameters means epsilon 1 to epsilon 2. Connections are known for torus nodes. Connection is known. Epsilon 1, you transpose epsilon 1 and epsilon 2.
Sorry, what I'm saying is, okay, in this example, I didn't know the super polynomial,
Oh, yes,
right?
yes, yeah. Oh, sorry, A goes to A. A goes to A.
A goes to A and Q goes to 1.
And again, I already mentioned, but I need to say it again, that it is up to factor, up to power of Q, power to T. This is normalization to 1, you know, right?
Okay, but in this expression, Q
So
goes
1
to 1.
plus 1 divided by QT plus 1 divided by TA multiplied by QT, and you will get exactly this particular
Okay. And then a follow up question is that now if I want to take Q equals T.
Yes, half-life PT.
Yes.
This is for half-life PT. This is trivial. Q to Q minus 1. This is mirror.
Okay.
Just mirror, simple mirror.
Okay.
Right?
Then my real question is, can you explain the idea how you prove that the zeros of the Riemann hypothesis conjecture maybe in the previous
weak. How I proved it recently.
Yes.
This is the story is that I tend Q to 0 and carefully control modules which contribute, right? You remember it is about count of modules, right? It appeared that the limit, in a sense, the limit is a cyclotomic polynomial. Cyclotomic polynomial is good if Q goes to 0, as close as possible to 0. With some renormalization, the limit is cyclotomic polynomial, right? Then there will be square because of some reasons. Anyway, it will be some square roots of unity. All of them, of course, complex number modulo 1. Not modulo 1, modulo 1 divided by square root of Q. Right? But on the other hand, there are two important things. First of all, cyclotomic has all roots which are modulo 1, and second, all roots are simple. Then just standard deformation argument for small q's will be the same. Because there is a reality argument, right? It's always with zeta. If you have z is 0 zeta, then z bar will be 0. I combine z bar, right? And then I see duplication of zeros, right? Which is impossible because cyclotomic polynomial has all simple roots. This is how it works for small q's.
Okay, do you have a reference? Yeah.
Coffee break, guys. We can talk. Yeah.
Maybe if there is one more quick question, we can.
So I wonder this for plane singularities, the gap sequence, does it completely determine the singularity?
Oh, yes. If you know gap, you know gamma. If you know gamma, you know everything, right? With reservation about the intersection, but you know this stuff. Intersection numbers must be calculated. Yes. Very nice combinatorics, right? And definitely there are some links to what you are doing, right? But we need to talk. Right?
Okay, so let's thank the speaker once again.